Hello and welcome to our 19th video on derivatives of logarithmic functions. Our main focus will be on the natural log and its derivative, but at the very end we will discuss other logs as well. Natural log is our most common one though. The derivative with respect to x of natural log of x is 1 over x. Not too bad. Now, of course, this gets a little more complicated when chain rule is involved. So let's take d dx of ln of 2x minus 7. So notice the input is more than just x, it's a whole other function, 2x minus 7. So this is chain rule. We have function composition here. We have a function being plugged into an outside function. So the way that we handle this is we take the derivative of the outside function first, but leaving this input intact. And then we multiply by its derivative. So treating the outside first. The derivative of natural log of just x is 1 over x. So we get 1 over, well, not x in this case, but this whole input. But then, by chain rule, you have to multiply by the derivative of that input. So, just chain rule, that's what I've done. And the derivative of this is just 2, so I'll go ahead and write it up in the numerator. And there we go. Now, let's do natural log of a square root. Find f prime of x for f of x equals the natural log of the square root of x plus 3. Now, technically, this is the composition of 3 functions going on here. I have the square root plugged into the natural log, but even the square root itself has another function inside, x plus 3. But we don't have to worry too much about it, just take it one step at a time. You can just keep doing chain rule again and again. I'm actually going to solve this in 2 ways. I think both are useful for us to look at. So method 1 will be chain rule immediately. So f prime of x, derivative of the outside function is ln. So 1 over my input times the derivative of that input. And now here is where we do chain rule again. Right, this also is a chain rule problem. Since my outside function is a square root, I use power rule on that because remember, square root is to the 1/2 power. leave the x plus 3 alone. That's chain rule. And then you multiply by the derivative of the inside. So we had to do chain rule twice here. Now, notice something interesting. So I've got a square root of x plus 3 in the denominator. Because this is to the negative 1/2 power, that's also square root of x plus 3 in the denominator. So I'm multiplying the square root of x plus 3 with itself. The square root goes away. So there's just an x plus 3 down here. And I'll throw in the 2 as well in the denominator. And the derivative of x plus 3 is just 1. And now I can distribute the 2. So there's the derivative. It's surprisingly nice compared to how nasty the original function is. So that was one method where we did chain rule right away. We actually did chain rule twice because this little derivative was also a chain rule problem. I want to show us another method just to show that there's more than one way, and it's also a good way. Method 2, we will take advantage of log rules. So a log rule first. To start the problem before you even take a derivative. So I'm not yet taking a derivative. I'm going to rewrite the function to make it a little better to work with. So instead of writing it as a square root, I'm going to write as an exponent to the 1/2 power. And recall, one of the log rules is that whenever you're taking the logarithm of an exponential, that this power can move outside. So again, I haven't even taken a derivative yet, but I've rewritten the function so that its derivative will be easier. This is a lot less complicated than the natural log of a square root. We get 1 over x plus 3 times the derivative of x plus 3. It's just 1. And this is the same answer that we got with the first method. That means we probably did something right. Both methods are valid. They're both good. It's good, I think, for you to understand both of them. Then you'd be in pretty good shape. Next, let's take the derivative of y equals negative 3x times ln of 9x plus 1. Notice there's a product here. So when I take the derivative, dy dx, I'm doing product rule first. And I'll show extra work. So derivative of the first one times, leave the second one alone, and plus the reverse. leave the negative 3x alone, times the derivative of ln of 9x plus 1. Okay. Minus 3x, and this derivative, because the outside function is natural log, start with 1 over the input, then multiply by the derivative of that input, 9. And then just a little simplifying to do, it comes together as minus 27x over 9x plus 1. And there it is. So the big thing with this one is that we had to do product rule because that's a product. And so we can't forget about that rule as we move on. This is a cute little example. So then find dy dx. I'm going to show two methods on this one too, but it's pretty quick. Method 1 is to recognize that this expression can be changed into something very simple. E to the ln of x. Because I have the natural log function plugged in to the exponential with e as the base. Remember, ln is base e. So these are compatible. They have the same base. That means they cancel out. These are reverse processes being applied to each other. We cancel to just x here. So a little bit of a trick question. It's made to look very complicated, but e to the ln of x is just x, turns out. Assuming x is properly in your domain. But that's kind of assumed from the start. So I wouldn't worry about that too much. But we do need x to be positive because it's getting plugged into ln. Well, because this thing is just x, when it's defined, that is, then dy dx is just 1. And method 2, for the sake of practice, let's just try to take that derivative using chain rule. So y equals e to the ln of x, then dy dx. My outside function here is e, or yeah, this e in particular. E is my outside function. So we take its derivative first. Remember, the derivative of e to the x was just e to the x itself. Although in this case, ln of x is the input. So I've just taken the derivative of the outside function, leaving this input intact. And then you multiply by the derivative of that input. So I've just done chain rule here. So e to the ln of x times 1 over x. And okay, now it would be nice to use the identity that this is just x. Again, assuming x is a positive number, otherwise this is nonsense. But I wouldn't worry too much about that. This will be a little bit of more challenging problem. I keep bringing tangent lines back because they are very important. I'm going to find the equation of the tangent line to the curve y equals, and here's a fraction, 4 times ln of x plus 2 over x squared. And I need to say a little more because remember, there is not just one tangent line to a curve, but rather there's a tangent line for each point on the curve. It's a line that just glances the curve. Why don't I give a quick illustration? I'm not saying the function looks like this, but if I look at this point, boom, there's a tangent line. There's also a tangent line that's separate at this point. Just glances the curve there. So my point is that I always need to add a little more. I cannot just say, find the equation of the tangent line to the curve. I have to say, at what point? Well, this will be at the point -1, 0. And you can check that this is indeed a point on the curve. Now, I'm going to introduce some new notation, but it's not a new idea. It's just new notation for it. The slope of the tangent line is the derivative evaluated at that point. Like, that's nothing new, but this is new notation for it. So dy dx is the derivative of y with respect to x. When you're trying to evaluate it at a particular point, you draw this big vertical bar next to it, and then as a little subscript next to it, you write the description of the point. In this case, it's the x value that matters. So the derivative of y with respect to x evaluated at x equals -1. Remember, the derivative alone will tell you the slope of the tangent line at whatever point you're concerned about. But we're looking again at a particular point. So we evaluate. Let me write that down real quick, what this means. The derivative of y with respect to x, that means x is the variable. But then evaluated, so you're plugging in something at x equals -1. So this is just like when we did previous iterations of this problem. Think of it like f prime of -1. The derivative, but you're plugging in a point. or x value. The reason I did not use this language for this problem is because I'm not talking about an f. I'm using the language of y, but it's really the same thing. I'm just being a little more consistent with my notation, sticking with the y notation for this problem. Okay, so we need to take a derivative. We'll take the full derivative first, and then we'll just plug in that x value, -1. Okay, so here's my y. We're taking the derivative of that. That looks like a quotient to me, right? We've got that big division bar. So I have to do quotient rule first. Low d high minus high d low over low squared. That's a little too much there. Okay. I do want to see that actually. Low d high. I'll show my extra work here. Minus high d low all over low squared. Okay, now I don't need to zoom up again. Or scroll up, rather. We have x squared times this derivative. That 4 will just be strung along. It's just a scalar multiple. So ln is the outside function here. This is chain rule. I have x plus 2 plugged into ln. So it's 1 over that input times the derivative of that input, x plus 2. And the derivative of x squared is 2x. And this next part, normally I wouldn't do this, but since this is pretty easy, we'll actually square that out. It's when you have something like x plus 1 squared or something like that, that we usually don't bother to actually square it. We just leave it written as squared. But in this case, it makes all the sense in the world to multiply that out as x to the 4th. Remember, with the exponent rules here, you multiply in this case. So 2 times 2 gets me 4. The reason we do this is we'll be able to cancel with what's written above. Let me clean this up real quick. This derivative of x plus 2 is just 1. So that's a times 1. I don't need to write it anymore. Might leave this as is for the moment. And I can bring this 4 and 2 together as an 8. Notice that both of these functions, or both of these terms, I should say, have an x in them. So that can cancel with one of these x's down here. Oh. So we can only cancel one of them because I only have one x here. So that cancels. I might want to use a different color just because this is a little hard to see. There, that becomes a 3 power. And one of those will cancel. Now I'm going to follow what Pearson did for this problem with how they simplified. They chose to bring this x plus 2 down into the denominator, which is fine. You just have to be careful about it. So x cubed times x plus 2. So move that down. If I'm going to do that, I have to account for it in this other term. Right, so I have to multiply this term by x plus 2, since I put an x plus 2 down here in the denominator. Let's say times ln of x plus 2. If you're confused by that step, it helps to think backwards. So going from here to the previous step, well, if I didn't want this down in the denominator, I would cancel it from this term. But there is no x plus 2 up here, right? And so I'm still dividing by x plus 2 there, so I would have to leave it like this. So this is just how Pearson chose to simplify it. So I'm showing what they did. It's a bit of a confusing step. But it comes from the fact that I have an x plus 2 that I'm dividing in this term. And there is not one over here. And I wanted to write it in the denominator, so I moved it down. You just have to account for that in this term here. So we threw it in. Me personally, I would be fine with this, leaving it at that step when you're done canceling, but just wanted to show you what Pearson did. Now, I made a mistake by circling this because we're not done yet. Now, that was the hardest part, but we just found the derivative. Remember the goal of this problem? We're trying to find the equation of the tangent line. The purpose of finding the derivative was to get the slope. We still have to evaluate it. So now I have the general expression for the derivative. This will tell me the slope of whatever tangent line at a particular x value. I would just plug in the x value here. So that's what we'll do. When the x value is -1, we plug in -1 for x. Now you can save a little time by noticing that this ln here is ln of 1, and that is 0. So I'm multiplying this part by 0. That makes that entire term 0. So really all that remains of the numerator is this negative 4. And this is a positive 1 times a negative 1. So cancels to 4. So this is the slope of my tangent line at this point. Now we're almost done with this. I now have a slope of the line that's 4. And what else do I know? I know a point. We were told it's negative 1, 0. That's given in the problem. It's the point on the curve that the tangent line is at. That means it's also a point on the tangent line. So I have a point and a slope that is point-slope form. Y minus the y value equals the slope times x minus the x value of the point. And we can simplify this. X plus 1. And then if I distribute that 4, then I'm in slope-intercept form, which is nice. The y equals mx plus b form. So that's the tangent line at that point. Now we've been spending this lesson on the derivative of ln, natural log in particular. But let's take a little time to look at other logs as well. Well, you need to have your base greater than 0, so positive base, and not 1. And typically we'll choose things bigger than 1, but this formula does work in general beyond that. So log base a of x, this is any logarithm so its derivative will look pretty similar to the natural log formula. Remember, natural log is just the 1 over x part. And the reason it works for that too, remember natural log is log base e. So this a here would be e, and ln of e is just 1. So this formula works for ln as well. This is the more general version. Let's do a couple examples with this. Looking at log base 6 of x, taking its derivative is just 1 over natural log of 6 times x. This one will be a little more complicated. Let's take the derivative of log base 2 of x cubed times e to the x. Now, I suppose we might be able to do a little bit by taking advantage of the log rule when you're taking a log of a product. But I'm going to skip that. I've done plenty of two-method solutions today. So let's just not use log rules here, but we'll do chain rule instead, because I have function inside the log function. That's chain rule. Log base 2 is the outside function. So it's 1 over, don't forget your ln of 2, because we're base 2, times the input is in the denominator as well. And then you multiply by the derivative of that input. Looks like a product rule to me. We perform product rule here. So I take the derivative of x cubed, then multiply by e to the x left alone, plus x cubed left alone times derivative of e to the x. Well, that's actually just e to the x. Something that's nice to do now, notice that we have some common factors here, right? I have e to the x in both terms, and I have an x squared hidden in both terms. Let's factor those out. Factor out an x squared e to the x. When I do that, I'll be left with 3 plus just a single x left over. And that's over ln of 2 x cubed e to the x. Notice that we can cancel a little bit. Can cancel those e to the x's. This x squared will cancel. With the x cubed, we'll still have one of these left. And I'll just rewrite this as x plus 3 instead of 3 plus x. And there we have it.